Hello everyone, welcome to KLC 2022, the third Kuala Lumpur International Conference on Social Science, Education and Engineering. I'm Salinah Dullah. I'm from the Faculties of Engineering, University Malaysia, Sabah. Today, I'm presenting paper on the preliminary modeling of hydrological performance for green roof drainage layer using response surface methodology. Response surface methodology modeling is used in this study to investigate experimental results for waterproofing and drainage layers. The aim of this study is to determine the accuracy and the effectiveness of RSM through investigating the hydrological performance of green roof. It was proven that the mathematical equations developed by the RSM model are capable of predicting the outcome response, with ANOVA analysis being used to determine the level of the significant effect of the input parameter on the green roof hydrological performance. RSM models 2D contour plot and 3D surface plot expecting to reveal slope and water absorption, and this modeling shows significant effect on peak runoff, peak attenuation, and water retention. It is proven that the RSM can be used to investigate various factors affecting green roof hydrological performance. The global population is increasingly concentrated in urban areas. This has caused many problems for urban infrastructure and the surrounding environment, such as air pollution, urban heat island effects, and rainwater runoff, which have severely affected the environment of cities and surrounding areas. Because of this issue, many studies has been conducted regarding the green roof. One of the studies conducted by the Yuliani 2022 stated that the green roof installation benefits the environment by increasing biological diversity, reducing the effect of urban energy absorption, lowering building thermal temperature changes, lowering maintenance and operating costs from an economic standpoint, and providing social spaces where people have access to open spaces on the roof. The use of a green roof as a special expansion in building is not only for aesthetics reasons, but also attempts to address environment issues. Another recent study done by Menso 2021 stated that the urbanization has an impact on climate change, as evidenced by the urban heat island effect, as well as impact on urban noise, air pollution, and water management, all of which interfere with public health. Green roof material act as insulator in cold climates, reducing heat loss from inside to outside. As a result, installing green roof on building is one of the most suitable and effective ways of protecting the environment in order to achieve the United Nations Sustainable Development Goals. One of the most common methods for investigating the hydrological performance of green roof is through laboratory work. However, it is more time-consuming, costly, and complex. Modeling software, particularly response surface methodology, which is the RSM, is one of the tools that have been widely used for stimulation without needing to prepare an actual prototype. Based on study by Edwin 2020, the prediction on the parameters optimization can be obtained through RSM, and it could reduce massive laboratory work. What is actually green roof? Green roof is a layer living extension of the roof construction. It is natural, efficient, time-tested insulation methods. It has three types of green roof. The first one is the extensive, which is a low-lying under 6-inch performance-driven system. The second one is the intensive green roof, which is much higher profile, over 6-inch system designed for function and aesthetic goal in addition to core performance needs. The third one is the hybrid, which is the system employed facet of both. Green roof technology is a roof that contains plants or vegetation, and it may be fully or partially covered on the roof. We can see the figures in here. There is a few layers, which is the top layer is the vegetation, growth substrate, filter, fabric, drainage element, protection layer, root barrier, insulation layer, waterproofing membranes, and the last layer is the roof deck itself. Let's have a look on the overview methodology. The accuracy and the effectiveness of RSM in Minitab software we use to investigate the hydrological performance of green roof drainage layer for rubber crumbs, oil palm shell, and polyfoam. The input variables were slope and water absorption of the drainage layer. Meanwhile, the output variables, including peak runoff, peak attenuation, and water retention capacity. Mathematical equations developed by the RSM models are capable in predicting the output response, with ANOVA analysis being used to determine the level of the significant effect of the input parameters on the green roof hydrological performance. The RSM models 2D contour plot and 3D surface plot also reveal the slope and water absorption that have significant effect on peak runoff, peak attenuation, and the water retention. The analysis was performed using Minitab 18 software, which developed the response surface methodology model equation. The input parameter used were the test bed slope and water absorption of the materials. Meanwhile, the output variables that were selected are the hydrological performance, peak runoff, peak attenuation, and water retention. The RSM was modeled by using the experimental data obtained from ASMAN 2018. Table 1 shows a series of data set for each hydrological performance for modeling of the green roof drainage layers. RC representing the rubber crumbs, OPS oil palm shell, and PF is the polyfoam. Table 2 shows the parameter to be investigated. A. Slope, and B. Water absorption. The variance analysis for fitting the information to the second order and the contour plot will help to categorize the response surface. The Minitab usually compute the linear, quadratic, and interaction terms in the model. Verification of the RSM model performed at significant level of alpha equivalent to 0.05. This significant level indicates a 5% risk of concluding that a difference exists when there is no actual difference, and it's used to identify the experimental input parameter, slope, and water absorption. Result and discussion. The ANOVA test is used to determine the significance of survey or the output of experiment. In Minitab, ANOVAs compare the response variable means at different factor level to determine the importance of one or more factors. The p-value generally determines the significance of the parameters used for the input, which affect the output. The significant level of 0.05 was used in this analysis. Based on the result from table 3, 4, and 5, it's indicate that the linear outcome in the quadratic form are all statistically significant, which is p is lesser than 0.05. As for the two-way interaction between the two input parameters, they are found to be statistically insignificant, which is p representing more than 0.05. The experimental results from ASMA 2018 were used as comparison value to ensure the equation accuracy. The Minitab RSM model generates a mathematical equation for the output variables. The equation applies to water absorption, which ranging from 0.38% to 8.87%, and slope ranging from 0 to 6%. The model equation can be used to predict the hydrological performance of green roof, including pin runoff, peak attenuation, and water retention. Equation 1, 2, and 3 are the mathematical equation used to predict the hydrological performance of the green roof. If we look at the equation, A representing the slope and B representing the water absorption, both are in the percentage value. Tables 6, 7, and 8 show the comparison between the experimental value and the model prediction values, and the percentage error for the outcome, peak runoff, peak attenuation, and the water retention. And it is shown that the maximum value is below 13%. Figure 1, 2, and 3 display fitted line graph from the regression analysis for the hydrological performance. The summary model of regression analysis for all green roof hydrological performance model is shown in Table 9. It shows that the R-square value for each green roof hydrological performance are greater than 0.9, which is closer to 1. Peak runoff and peak attenuation have the greatest highest R-squared values of 0.9 at 6, while water retention has the lowest at 0.947. As a result, the predicted and actual value have good connection, and the regression model matches the data well. Based on the percentage obtained from the analysis, when the slope increases, the peak runoff rises with it, and the water absorption increases with it. According to ASMA experimental data, the greater the peak runoff, the faster the runoff time for water discharge from the green roof testbed. This is due to the growing slope of the green roof as well as the properties of the material employed as drainage layer, which are primarily concerned with water absorption to assess the hydrological performance peak runoff. Based on Figure 6 and Figure 7, which is representing the contour and the surface plot of peak attenuation, slope, and water absorption. When the slope is lower, peak attenuation and water absorption increases. According to ASMA, the higher the peak attenuation value, the more flow reduction and ability to attenuate the peak flow the material have. This is mainly due to the water absorption capacity of the materials and the slope itself, since it is likely to have influence on the peak runoff as well as the peak attenuation. As the slope decreases, the peak attenuation value increases. Based on Figure 8 and Figure 9, it can be observed that the water retention increases as the slope and water absorption decreases. This is because the higher water retention value, the greater the water absorption capacity of the material and the slope itself. In general, the retention value are determined by the properties of the green roof, which is the slope and water absorption of the material, being the primary determinant of the percentage of the precipitation stored in the test bed. Figure 10, 11, and 12 show the paragraph of the optimized data for each hydrological performance. Essentially, the Minitab optimization graphs show how the input variables influence the predicted response. According to Table 10, it shows that the greater the value of peak runoff, the higher the value of slope and water absorption of the materials. Meanwhile, as the slope increases, the peak attenuation decreases. As the water absorption of the material increases, the peak attenuation increases. However, if the slope and the water absorption of the material are higher, the water retention of the green roof system will be lower. As a result, of the hydrological performance of the green roof is influenced by both slope and water absorption. As conclusion, RSM model with Minitab software can be used to determine the hydrological performance of green roof. The output variables can be predicted using the desired input parameter. The amount of error for model analysis between actual experiment data and expected response of the output variables from the general equation range between -15% to 15%, which is considered acceptable and within the tolerance. As a result, the mathematical equations are valid. The R-squared value from the regression analysis for each hydrological parameter are greater than 0.9, which is closer to 1. The model created in the study are accepted because of the model is relevant when the R-squared is approaching to 1. I would like to thank the Research and Innovation Management Center, University of Malaysia, Sabah, for providing the financial support. If you have any question, feel free to contact me in this email. Thank you so much for your attention. I wish you all the best. Take care and goodbye.